Thanks so much, Chris. Yeah, hi everyone. Good evening, good afternoon, and moin moin to everyone. It's great to see so many new faces in the participant list. For those of you who don't know me, I'm Sven. I'm actually working in the optical, and what I'm personally very interested in is the Milky Way and its stars. So I'm here to give you a bit of an insight into the optical stellar spectroscopic perspective of multi-wavelength astronomy. And I think before we start, I think it's a really good idea to just take a step back and figure out how you and I see the Milky Way. Of course, on the night sky, we see this very nice optical Milky Band, but we all have different eyes. We have different telescopes with which we can see the Milky Way and all of its glorious content. And this is exactly where I hope we can get some connections today, both as part of my presentation, but also later with a few interactive segments. And of course, what I will focus on is especially stars and how I see stars and maybe how we can connect with how you see stars. And of course, across different wavelengths, you see stars differently in the X-ray, in the optical, or also in the millimeter and like radio regime. The same star, our sun, looks quite differently. There's a lot of detail that we can try to understand. But what I do actually is I take the light in the optical and I split it across the wavelengths. And if we do that, we get these beautiful spectra. And these spectra have in them kind of barcodes, these kind of wiggles that you see here, absorption features that really help us to figure out what's going on in the outer layers of a star, and specifically, how also do these stars move away from us towards us? What is their chemical composition looking like? Because these different absorption features are, of course, depending on how much of a specific element is there to absorb the light that tries to get out of the star towards us. And you can see that if you look at a periodic table, this is the way that I tend to look at this, because different elements have different wavelengths where they can actually absorb light. And this is cool because if you look at two different stars, you'll see that one of them has a lot of these barcodes. There's a lot of elements in a star that can actually absorb stuff. And if you look at a slightly less metal enhanced star, or a star that has a lot of these elements less, you see there is significantly less absorption going on. And this is exactly what I do in my day-to-day life, measuring how significant are these absorption features and try to figure out what we can learn about the chemical composition of stars. And I've done that not only for a few stars, but we've done that for millions of stars. And you can see one thing here, each of these rows are different stars. They wiggle around, they move towards us or away from us. But we can also measure these absorption features here in detail for a calcium line that has a nickel line next to it. And this is what we do in stellar spectroscopy. And if you do that for enough stars, you can really figure out how, for example, stars move towards us or how stars move away from us. You can learn a lot about the Milky Way as a galaxy, but also the individual stars or smaller galaxies, the galactic center, and a lot of substructure in the Milky Way itself. So that's one part you can do with stellar spectroscopy. And what we tend to do with a very specific survey that's called Galactic Archaeology with Hermes. It's one of these many optical spectroscopic surveys out there. And we have observed the southern sky with 1 million stars across different parts of the sky that you can ask me about why these are all so interesting. But one of the things that's quite exciting is that all of these stars have information from the Gaia satellite. So the Gaia satellite is basically mapping how stars move. So we get an idea of the two-dimensional proper motion of stars. We get an idea of the distance and of course where they are. And so GALA or optical spectra are basically delivering the sixth dimension to figure out how stars move in the future or the past. And in addition, Gaia also gives us an idea of how bright these stars are, what kind of color they have. And you all might have seen a color magnitude diagram with the main sequence and the red clump and a lot of stars that do a lot of different stuff. The great thing is all of the stars that we have observed are also mapped by this astrometric catalog of the Gaia data release 3. And so we can map on the left-hand side the photometric information that we have to what I as a spectroscopist care about, which is how hot these stars are, their effective temperature, and their luminosity or their surface gravity. And these are luckily linked. So you see that the left and the right-hand side look very similarly. So looking at stellar spectra, what we do is actually, we try to create models of these spectra And by just increasing or decreasing the amount of different elements or elemental abundances, as we say, we can basically get the best match and figure out the abundances of up to 32 elements. So on the right-hand side, I'm just showing you here, or in general, the blue and the black are basically our observation and our best match. And if you were to increase, for example, the amount of carbon, you would get a lot more absorption, right? So we can already see that the sun does not have 10 times more absorption in, or more carbon than the sun, but actually the solar abundance. You can do that for a lot of elements. I just want to show you how a spectrum looks like. There's a lot of wiggles, and this is exactly what allows us to map 32 different elements. But that's actually not really the focus of what I think is interesting for you if you're working in the X-ray or in the radio. But what actually might be more interesting to all of you might be the stuff that is actually not necessarily coming from one star. And one of the things that we can see is if we have a stellar spectrum and we have our observation and we look at the residuals, there's specific features that we actually know are coming from the interstellar material. They're called either diffuse interstellar bands, where we don't really know what their tracer is, or even better, on the very right-hand side, we have this kind of residual next to the stellar potassium line, which is actually coming from the interstellar potassium. And we've mapped that for almost 1 million stars. And the cool thing is that we can not only measure the equivalent width, or like the area of this line, which allows us to figure out the column density of interstellar neutral potassium, but we also get a line of sight velocity and a velocity dispersion. And this great thing then allows us to, for example, map the amount of absorption that we see between each of these 1 million stars and us, and really create this kind of extinction or interstellar absorption maps. So that's one thing that is quite exciting. And if you think about, okay, interstellar absorption, where else have we done that? Well, in the radio, we've actually done that. There's a lot of amazing surveys going on. For example, GasCap, which is actually a radio survey. And they have looked, for example, in regions a bit below the galactic plane. And what they have done is they kind of mapped the absorption or emission of neutral hydrogen. So where you see, for example, white regions here, you have more absorption coming from the neutral hydrogen. And we can actually compare the amount of neutral hydrogen absorption with the kind of absorption that we get from interstellar potassium in our optical spectrum. So on the right-hand side, in the top, I'm showing you what the radio astronomers would map with their emission or absorption features. And in the bottom, I'm just having an example here from the work that I'm currently doing with Heat Nguyen on the interstellar absorption from potassium from optical spectra. So you see, the great thing is they actually do match quite well. And we've done that not only for this one example, but we've done that for quite a few. And we've done the line of sight velocities of interstellar or the cold neutral medium that we trace with radio astronomy, and the optical part that we trace with the Galar survey. And if you not only map the velocity, but also you measure the amount or the column density of this interstellar potassium, what I'm going to show you on the left-hand side is basically a color map of where we find more interstellar potassium. And I'm going to just briefly show you. Yellow here means there's more interstellar potassium that we see in the optical. And remember, in the background, we have the radio. So if I'm just going back and forth, we're comparing the amount of interstellar potassium with the cold neutral medium. And this is something that I think is just amazing, that we have this combination between radio astronomy as a tracer of the interstellar medium and the optical. So this is one cool thing. And of course, I want you all to be able to do that. So we're going to look into this in a bit more detail in the interactive part. But another thing that we also do is we can look at peculiar stars. And most likely those could be stars that either have a binary signal, because they're actually not one star, but more, or they have some kind of emission. And that could also be emission, not only in the optical, but maybe also in the X-ray, maybe also in the radio. So I just want to equip you all with an idea of how do, for example, spectroscopic binaries look like, or how does emission in the optical look like, so that if you in the future look at a spectrum, you can actually say, okay, well, that's an emission star. So the first thing for binaries is, of course, they're orbiting around each other. So if you look, for example, just at the radial velocity of one of the components, either you see that as a function of time, it's actually changing, and you can map this, right? So here we just see the radial velocity as a function of the date, and you see that these the error bars are just moving up. So we really have a changing radial velocity. That's one type of spectroscopic binary that we can see. And another one is where we actually see a lot more absorption features than we would expect for a single star. And that is because we actually have a spectroscopic binary with line splitting. And we have now, as part of the Galactic Archaeology with Hermes survey, started to analyze these and are diving into the chemical abundances of the two different stars that contribute to the light of this binary system. So this is how a binary star looks like. And what happens quite often as well is that stars do some weird stuff. For example, if they're very young, they might have X-ray emission, they might have radio emission, but they also have hydrogen emission. For example, here in the H-alpha line, which is at 656 nanometers or 6,562 angstrom. That's kind of our unit that we work with. And you see in red is the fit that we would usually expect for a star with the stellar properties to look like. And then black, you see that this star actually is giving a lot of emission out there. So this is how you can spot an emission star quite easily. And you don't have to do that yourself, but we've actually tried to automate this process for you. But I would suggest if you want to figure out more about this, either ask me or read our manual of how we have done that. And I think now it's time to actually dive into the exciting part of if we have any overlap with either X-ray or radio. So one of the cool things is I'm showing you, for example, a globular cluster with a lot of stars, and some of them actually have X-ray emission. The question is, of course, have we maybe taken stellar spectra of them? Or there's also other amazing papers that have been written with eROSITA data. And as long as you, for example, have an identification in Gaia, we can actually check if we have any overlap with them. And if you're interested in radio data primarily, well, you could imagine to look at stars that might have radio signals, like radio stars. Laura Dreesen, who's going to talk tomorrow, has done an amazing study on those ones. And of course, we can check, do we have any overlap with them? And last but not least, there's a lot of stuff to do with the interstellar absorption that we see in hydrogen and potassium. So without further ado, I'm just going to switch over to the other notebook. And for those of you who have seen or opened the link, this is what it looks like. It's a GitHub repository. It has a lot of different notebooks, Jupyter notebooks that you can open if you have Python installed. Either you can just download them or just watch me doing it and then go back to it later. So I'm just going to start briefly with the overlap that we could maybe have with X-ray astronomy. So one of the things that you, of course, want to do is you want to first download the Galar data set. That allows you to actually figure out the identifiers that you then want to cross-match with. I've provided a very minimal example for you in the repository, but you can actually just read it in either by downloading the catalog, which is on this website here, or you basically just use the minimal example. And another cool thing that you can do is you can use a Python package that's called AstroQuery. That actually allows you to, for example, just go or pretend to go to the Vizier catalog server and just get a specific publication catalog. So in this case here, I'm just getting some candidate cataclysmic variables. And what I actually then do is just with a one-liner with the amazing AstroPy package, I basically just cross-match this publication with the one that we have from Galar because we have this Gaia data release free source ID. And well, you can imagine it's not super exciting to have three, but actually maybe three stars that overlap here are quite exciting. So you can see that some of these cataclysmic variables are actually below the main sequence. So there's a lot of very interesting stuff going on. And what you can also do is you can actually download the data product. So you can download, for example, the spectra. You can get an idea of the radio velocity fit that we've done to just convince yourself that this all looks reasonable. And I'm just providing here the way to do that automatically, so you don't have to do that yourself. Of course, I've done that beforehand, so you don't have to do that. And what you then can do is you basically just plot the spectra. And I'll not bore you with the details of how to do that. It's all hidden here. But basically what we do with the stellar spectroscopic survey that we have is we have 4 different regions of the optical spectrum that we cover. And you see that this star here is actually looking very, very different from this star here. But this one here looks very, very similar to the sun. You have these 2 significant absorption features here. That is H beta and H alpha. This one actually doesn't look all too crazy, but we know it's actually a binary. This one here does a lot of crazy stuff. First of all, you see that we have actually gotten the radial velocity of this star wrong because this is H alpha emission and this is H beta emission. So this is a bit of a warning sign. This star would actually be flagged as unreliable, but you still have some cool information on what's going on with this star. So another thing that you can do is you can, for example, try to figure out an overlap with this amazing work from Freund et al., different Vizier catalog, and it's downloading now. So it has downloaded in the past. You see, there's actually a lot more going on here. And we can then try to understand all of these sources. Where are they actually in either the column magnitude diagram or in our temperature log G space? And you see that a lot of them are close to the main sequence. I'm actually providing here just a zoom of this so that you can follow my description here. One of the things you see is there's stars that are in this slightly shifted region. They're just slightly above what we typically would say is the main sequence. And this is because most likely a lot of these stars are actually binary stars, right? They're more luminous than we would expect a single star to be. And then there's a lot of stars in this region here, and this is especially the pre-main sequence or young star region. So there's a lot of cool information you can get out of the photometry already, but also the spectroscopy. And then if you're interested in stars in old clusters, like the Global Cluster 47 TUG, you can do the same thing. You can download it, and you'll actually find that out of all of these stars that we have observed with Galah and this X-ray study by Saidi et al., there's actually at least 8 stars overlapping. So there's a lot of stuff, and this can just get you started if you're very, very much interested in X-ray analysis. If you're interested, for example, in stars that have radio signals, well, we also got you covered. So you can do the same thing. You basically just import your packages. You have Galah DR4 that you basically just download here. And then the same thing, Laura's work is published by the publications of the Astronomical Society of Australia. So you can just get this catalog as well from the Vizier. And you can just make sure that you actually have only sources that have Gaia identifiers. And then you do the same thing that you did before. You just cross-match them with Galah. And if you say, well, I want actually more information, there's much more to do. I'll just quickly run through this, but you'll have all access to the links here. So one of the things you can also do is you can actually upload either Laura's table to the Gaia archive, and then basically just cross-match and get additional information. So I'm just providing all of this for you here. If you have never seen an SQL or ADQL query, you've heard from Grzonkin before. This is actually how they look like, and this is exactly how they're executed. So you basically just write this and then feed it into this Astro query service. And you'll see that actually, first of all, there's 820 or a few more stars that overlap between Gaia and the radio stars that Laura has identified. But also, if you then look at the overlap between the Radio Gaia catalog and Galah All-Star, you'll see that there's 42 stars, which I think is a perfect number to continue working with. And one of the things you can, for example, ask yourself is, well, what's going on with the radio velocities? Both the Gaia satellite also has a spectrograph on board. So you get a radio velocity both of Gaia and Galah, and you can actually check the difference. So one of the things that you can just plot here is the difference between the radio velocity or the line of sight velocity between one spectroscopic survey and Gaia. And typically we know that the uncertainty of Galah or Gaia in both cases is actually less than 5 kilometers per second. So if you have a difference that is more than 40, that's quite significant. So a lot of these are actually showing radio velocity variation, which is quite exciting. You can also check, for example, for stars that have not only these radio velocity differences, but also H-alpha emission. We have, for example, a measurement of how much H-alpha emission we have. If you say, well, it has to be at least some sort of emission, you can just easily identify these stars and then just plot them in the column magnitude diagram, as I've shown before, or the temperature surface gravity diagram. And you see not only all of the stars that Laura has identified, but you also see the stars that we have observed with Galah. And a lot of them, or almost actually all of them, have H-alpha emission, and a lot of them actually also have changing radio velocities. So this is quite interesting, but of course, we're thorough astronomers, so we want to convince ourselves what's going on here. So as before, we're just going to try to download the data together. And well, I've done that all for you. It's already here. So what you can do is actually just for 2 examples that I wanted to show you, you can just plot the stellar spectra of 2 radio stars. So the first one at the top, you see a zoom into the H beta region, the H alpha region, the lithium line, which lithium is actually an indicator for young stars, and then also something around the interstellar potassium line. And you see that this star has a lot of lithium. And this is interesting because only or almost exclusively only young stars have a high amount of lithium. And you also have some sort of absorption or emission in the AH alpha region going on. So that most likely is a young star, pre-main sequence star. And the second star that I should have said, this star is also known as a double star. And the second source that we have here has crazy amounts of emission that is quite different from what we would expect for a normal star, both in the H beta and in the H alpha. And you could actually measure that yourself if you wanted to. There seems to be something crazy going on also in the lithium region. We can't really measure this well. So this would be most likely flagged as unreliable. And there's a lot of crazy stuff also going on around the potassium feature. And this one is actually known as an X-ray source from the Rosette observations. So this might also just get you started if you're interested in radio stars that maybe also have some X-ray signal. And last but not least, for the radio astronomers among you, I wanted to show you some of the really cool things that you can do if you're interested in galactic archaeology and understanding all of the stuff that's going on in terms of the gas inside of our Milky Way. So the same thing is, as always, you can download the Galar data. And one of the things that you then are interested in is not necessarily the radial velocity of stars, but you can again look into the potassium line. And one of the most mind-blowing pieces of information that my radio astronomy friends told me is that the radial velocity notation is actually different between radio astronomy and optical astronomy. Because some of you use frequency and we use wavelength. So you always have to be a tiny bit more careful when you want to make high precision velocity comparisons. But once you've done that, you can actually do some coordinate transformations that are nicely hiding between some of these lines here, and actually plot, for example, the line of sight velocity of interstellar potassium as a function of the galactic longitude. And you'll see there's a lot of absorption happening that is moving very, very similar or very close to zero. There's some weird stuff going on in the lower region here, and this is especially where we have to be careful because we don't really expect a lot of material to move like this. You can also zoom into this region that has a lot of this absorption and see a lot of amazing substructure. So if you're a radio astronomer, it would be great to have a chat in what you see here versus what I think I see here. And last but not least, you can also move from a line of sight velocity to the local standard of rest velocity, so just an additional transformation. And then you can actually have something that you can compare with the way that radio astronomers typically plot these things. But I also just wanted to come back to this weird stuff that's happening here, because you always have to be careful and thorough to check that what you see is actually reasonable. So you can, for example, compare different tracers in the optical of the interstellar medium. We have both potassium, or K, and we have interstellar bands, diffuse interstellar bands called DIBs. And what you want is that they are all kind of similar in terms of their velocity. So if you just plot a one-to-one comparison between these different ones, you want to have a line that is basically going from the bottom left to the top right. But in some cases, you see here, there are some lines that are offset. And this is because you can imagine that some features we just don't measure right. And they're always off. They're typically coming, for example, from stellar absorption that we just don't model properly. And this is a way how you can actually clean your selection to be only left with the actual reasonable and reliable sources. And what you then can do is, if you haven't had enough yet, this is the last plot I wanted to show you. You can actually, for example, look at the amount of interstellar absorption, the line of sight velocity, and also, because we actually have a lot of these sources, the line of sight velocity dispersion. And you can not only do that for a map, but actually because we have stars, we have an idea of how far this absorption happens. So we have an idea of the distance of the star, so we know the absorption must happen between us and that star. So we can actually say, if I only want to look at the absorption between 0 and 500 parsec, or 500 to 1,500 parsec, or for example, 1.5 to 2.5 kiloparsec, where's this absorption happening? There's a lot of additional information that optical astronomy can give you. And hopefully this is all quite exciting for you if you're interested in starting to compare X-ray, optical, and radio astronomy.